Now we go on to the last part. We talk about the heating and cooling curve. Okay, now this is what we call a heating curve. It's actually a graph which shows how the temperature of a substance, okay, changes as it is heated. So it's actually a graph of temperature against time. Okay, temperature against time. So generally, if you see every time when it goes through, when it has a flat line, remember there's a change of state here. You can see another flat line here, there's a change of state over here. Okay, now if you can think about it this way, if there's two change of states, the final state, okay, because you only got three states of matter, isn't it? Okay, so if you have two change of state, means most probably all three states must be here. At a higher temperature, definitely this should be a gas. Okay, at the starting part, it should be solid. Definitely in the middle here, it will be a liquid. So you can see that actually, when there's a slope, okay, there's only one state existing. But how about in the middle here? Because there's a change of state, okay, there's actually two different states present. Your solid, during this stage here, is actually solid plus liquid, because your solid is melting. Obviously, from solid to liquid, what is this change of state? This is actually the process of melting. Same thing here, liquid changing to gas. So definitely we have both liquid and gas present here. What is this change of state? It's actually your boiling. Okay, boiling over here. So now let's look closely in terms of the kinetic energy and potential energy. How does it work over here? So in region A to B, okay, let's try to have them both together. Okay, now, so I managed to put a little diagram over here. Now from region A to B is at this part over here, this region over here. Let me use a different color to shade here. Okay, this is region A to B. Okay, so at this point here, because the temperature is increasing, the kinetic energy increase. So as I was saying, Ke is related to temperature. So when the temperature changes, the Ke changes. So when the temperature increase, the K increase. And when the K increase, actually the potential energy remains constant. Okay? In this state, if you look at all across all of this here, you realize that, hey, when one of them increase, the other one is constant. Okay, so just remember, only one of them changes each time. So in this case here, from region A to B, we say that the kinetic energy increase, but the potential energy remains constant. As I've said just now, only the solid state is present. From B to C in the melting process, okay, the kinetic energy remains constant because the temperature is constant over here. This is region B. Okay, the kinetic energy remains constant because temperature is constant. Whereas for potential energy, this is where it starts to increase. Okay, what is the potential energy used for? It's used to overcome the force of attraction. At this part here, both solid and liquid state is present. Next one. Okay, we have the liquid state. Okay, maybe I shouldn't use this color. Let's use green color. Okay, for the liquid state, C to D. Temperature increase, definitely kinetic energy increase. Potential energy remains constant because K is increasing. Okay, as I was saying, only one of the energy will change at each time. And at this point here, only liquid is present. And the last one, we talk about D to E. Okay, D to E over here. We say that the kinetic energy remains constant because temperature is constant, but the potential energy increases. At this point, only liquid and gas is present. And the last part, we talk about E onwards. Okay, only gas is present. At this point, temperature increases, so kinetic energy increases too. So this is how you can look at the heating curve in terms of your kinetic energy, potential energy, and the states present. At each point, you can also know what states of matter is present. You can also know what is the process that's occurring. Okay, you must always know what is the process occurring at each of the flat line. It will help you to differentiate what states of matter there is. Okay, now the next one we go into is the cooling curve. This is exactly opposite of the heating curve. This is where we talk about how the temperature of the substance changes as it is cooled. Okay, as it is cooled here. So once again, temperature versus time. Let's draw the same few thing here. We split it into different regions. Okay, this is a change of state. Okay, this is also another change of state. So, what is actually occurring here? You can see that there's two different change of states. So obviously, as I cool things down, the last state, if I finally cool it down and temperature drops further, this must be the solid state. So at this state here, it must be the gaseous state. Temperature changes, so in the middle, this must be the liquid state. Okay, at this point here, must be definitely liquid plus gas. This must be liquid plus solid. So this is the change of states. Okay, when we talk about how to find out where's the states of matter, we talk about how to find out all of it here. Okay, now let's go on to look at the table once again. Okay, now we're gonna go into the next part. Okay, where you can see here, really we're gonna go into describing the cooling curve. So let's once again look at region A to B, which is this region over here. Okay, in this case here, only the gas state is present. Now, obviously, as once again, I need to put it across. Remember, temperature is related to, KE is related to temperature. Okay, so you can see here the temperature is decreasing, so kinetic energy must be decreasing too. For K, however, remember I was saying also that if one of the energy changes, the other one remains constant. So if the kinetic energy decreases, potential energy must remain constant. And the state of matter present here is gas only. Now, from B to C, over here, we know that the temperature is constant, so a change of state must be occurring. In this case, it's the process of condensation, because it is from gas to liquid. Okay, gas to liquid. Okay, as the temperature is constant, so Ke remains constant. In this case here, potential energy decreases. Definitely when you're cooling something down, okay, the energy should drop. So in this case here, the potential energy is the one that's actually decreasing. The states of matter present now is gas and liquid. The next one we talk about is region C to D. Okay, kinetic energy here now is decreasing because you can see the temperature is decreasing. The potential energy remains constant, and that's liquid state only. Now from D to E. From D to E, there's a change in state because the temperature is constant. In this case here, we know it's from liquid to solid, so we say that this is thus freezing. Okay, as temperature is constant also, we know Ke is constant. Potential energy actually decreases. Okay, at this point here, decreases. And what are the states present? You got liquid and solid. Now, last one, E onwards. Okay, for E onwards, okay, temperature is decreasing, so Ke decreases, potential energy remains constant, and the state present is solid only. Okay, so this is in terms of the cooling curve and the heating curve. These curves are actually important because it does help you to determine what state is present. It tells you when is the change of states and whatsoever. Okay, questions like this will tend to come out. They will not ask you to fill up a table, okay, but they'll ask you what is happening between the process between B and C. Definitely ask you condensation, so you must know how to describe what happens during condensation. So same thing here, I can ask you what's happening between D and E. Okay, D and E. They must tell me boiling. So what's happening to the particles at boiling? So then you have to go all the way back to this slide, and then you have to talk about all of this. So this is how you use your heating and cooling curve. Okay, now this marks the end of KPT, and we'll move on to the next chapter next time. Okay, so see you soon.